welcome back to my channel. I hope everyone is doing great. Let's solve fifth problem of dynamic programming study plan. Okay, the problem statement states you are a professional robber planning to rob houses along the street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have a security system connected, and if and it will automatically contact the police if two adjacent houses were broken into on the same night. Okay, if you rob two houses which are adjacent to each other, then police will be automatically contacted and then you will be caught. Given an integer and a nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Okay, you have to rob the houses in such a way that you get maximum money. Okay, so for a given house I have two options: either I can rob it or I cannot rob it, or I choose to skip to rob it. Okay, let's look at some of the possibilities. Let's say I've chosen to rob the first house, then I cannot rob the second house because if I rob second house as well, both the houses will be adjacent to each other and police will be contacted. So I should skip to rob the second house. Since second house is not robbed, I can rob the third house and then I will skip the fourth house. Okay, this is one possibility of me robbing the houses. The second option, the second possibility is I choose to skip the first house and I will be robbing the second house. Okay, and then since second house is robbed, third house should not be robbed. Then I can rob fourth house. That is what here we are seeing. Let's look at one more possibility. I choose to skip first, second. I'm robbing the third house and I cannot rob the fourth house because third is robbed. Okay. So let's define a recurrence relation which will tell me the maximum amount you can rob safely. Okay. So the first option is basically I choose to rob a particular house. Okay. If I choose to rob a particular house, then the amount which I will get is nums of 5 plus f of I plus 2. Because I cannot rob the second house, I have to rob the house next to it. So that is what I am doing here. So I am robbing the ith house, then I cannot rob the I plus 1 house, and then I can rob I plus 2 house. So this will tell me the maximum amount I can get by robbing from I plus 2 house till all the way till the end. Okay, the second option I have is to skip the current house to rob. Okay, if I choose to skip the current house, then my answer will be coming from robbing from I plus 1 houses till the end. So f of I plus 1 is the second option. So my answer will be maximum of these two options. So I will be taking the maximum. Okay, so what are the base cases for our recursive relation? Okay, if there are no houses to rob, then the answer will be 0. Okay, that is the base case. Okay, let's try to look at the tree diagram for our recursion. Okay, if you see f of I is depending upon I plus 1 and I plus 2. Okay, again I plus 1 is depending upon I plus 2 and I plus 3. I plus 2 is depending upon I plus 3 and I plus 4, and so on and so forth. Okay, there are certain function calls which are repeating, so I don't have to recompute the answers which were already computed previously. So I will be caching these values and then reutilizing whenever it is required. Okay, so this approach is known as dynamic programming. Let's look at the implementations of our problem. Okay, so since I have written the recurrence relation, okay, you can implement the top down approach, but I will be showing you the bottom up approach. Okay, if you keenly observe, our states are filling from in the backward direction. Okay, so let's say I have a dp array of n plus 2. So first n minus 1 array is getting filled as per this recurrence relation, and then n minus 2, n minus 3, and so on and so forth. Okay, so we will be also filling our dp array in the same fashion. Okay, I will be filling dp of I with dp of I plus 1 comma nums of I plus dp of I plus 2. This is basically skipping the ith house, and this is basically the robbing the ith house. Okay, and I will be doing this from n minus 1 till all the way to the 0. Okay, and my answer will be lying in dp of 0. Okay, so if you submit this, the answer will be satisfied and all the test cases will also be passed. And if you analyze the time complexity of this approach, it will be big O of n, and space complexity is also big O of n because we are using a DP array of size n plus 2. Okay, this can be further optimized in terms of space complexity, because at any given state for any given I, it is only depending upon I plus 1 and I plus 2. Okay, so I will be having two variables called next one and next two, which will be storing the values of these two values which were computed previously. So initially these two will be 0, and then I will be going from n minus 1 till all the way to the 0. So currently if I choose to rob the ith house, then I can if I skip, then my answer will be presenting in next one, or if I choose to rob the ith house, my answer will be nums of I plus next of 2. Once I have done calculating robbing the ith house, so the next one will become next 2, and current will be becoming the next one. Okay, for the next value of I. So in the end my answer will be presenting in next one. Okay, if you submit this problem, okay, all the test cases will be passed, and it will be pretty efficient solution in terms of both time complexity as well as space complexity, as you can see. So the time complexity here will be big O of n, as we are running a for loop from n minus 1 till all the way to the 0, and the space complexity is basically big O of 1, because we are just using some variables to compute the results. Okay, that's all about this problem. If you like the explanation, hit the like button and hit the subscribe button, and also share your valuable feedback in the comment section, and don't miss to subscribe, because we will be solving all these problems in our series. Okay, thank you.